I'm Christopher Meiklejohn. I am a Ph.D. student at Université catholique de Louvain and Instituto Superior Técnico in Portugal. And basically what I'm going to do today is talk about some research that has been coming out of a bunch of these universities that we're affiliated with. So some universities in Portugal, and then in Belgium, and then in Germany, and Paris, and some other places. And it's basically on addressing kind of the problem of making the choice between CP databases and AP databases, and kind of where we can go from there. So, catchy little title, Closing the Cap Gap. So what do we mean by this? So just to provide a general outline of the talk, what I'm going to do is convince you, or try to convince you, of a novel approach of dealing with consistency in distributed systems. This is something that our group's come up with. It's called just right consistency. And basically, the gimmick is that we want your systems to be available whenever possible, while acknowledging that sometimes you have to coordinate to enforce an invariant. And so we're going to show ways to identify those invariants that you need to coordinate for. I'm going to talk about a database called AntidoteDB. This is a database that we built in Erlang. It's kind of a research prototype at this point that we're working on industrializing. And this is the first database that takes a step towards providing an actual thing that you can use that has what we refer to as this design philosophy, just right consistency. And then finally, I'll just briefly talk about what we're doing in terms of research and what we're doing in terms of industrializing the research products, the research artifacts into industrial artifacts. All right. So to kind of motivate the talk, basically. For the past 10 years and going back to the 80s, the way we've developed applications is that we kind of, we choose some place to put a data center and some server. So here I've chose, arbitrarily US West 2 in the AWS region, and I've placed all my data there. So I have data center A. And all of the users who are using my applications, whether they're on mobile devices or they're running web browsers or whatever, are communicating directly with this database. So they're modifying data directly in this database. This database serves as the primary copy for all of the information. Now, this is problematic because, as you can see, these are very long lines. And some of these lines mean that the fastest you can possibly do this, if you can send data at the speed of light, is something like 152 milliseconds or something like that. And so this is problematic. And so what in addition to failures and connection failures and things like that. And so what a lot of people have been doing is trying to geo-replicate their data, so place copies maybe in the Dublin region on AWS and the Singapore region. And we do this for a variety of reasons. The first is usually fault tolerance. We want our applications to continue being able to make progress when potentially one or more can't contact each other. We do this for high availability in case for some catastrophic reason, data center A goes down, Netflix still wants to be able to serve data out of data center C, so everybody can keep watching House of Cards or something like that. And finally, kind of one of the major motivating factors for a lot of application developers are that clients can read and write against their local replica. And so here, clients that are located in the western part of the United States can talk to a data center in Oregon, where clients that are located potentially in Scandinavia can talk to the Dublin data center. So there's low latency. And obviously, I skipped the other kind of important concern here, which is security. So that's another thing. If you're in the European Union, then if you live in Europe, then you know that there's some pretty interesting privacy laws we have to adhere to there. And so the problem that we have as developers of distributed applications and as of people who write distributed databases is basically when C cannot communicate with A or B because of a network event, we have to make a choice. And so there's two choices, or historically there have been two choices, kind of falls under this idea of cap. And the first choice is we can remain consistent under partition. And so this means that when C can't communicate with A or B, I will refuse the operation. I will not allow the operation to proceed because I want to maintain what's referred to as a single system image. And so this means that even if I have a database located partially in Dublin, partially in Singapore, partially on the West Coast, or fully replicated in those three locations, I want all of those databases to look like one logical unit, one logical database. And I never want to deal with the anomalies that come from not synchronizing. So we synchronize for every operation we do on the database. So what are some databases that provide this single system image? Famously, there's Google Spanner. They do this through GPS transceivers and atomic clocks to try to determine how closely they can synchronize clocks in the window of uncertainty so that they can run geo-coordinated transactions. Another database that does this is CockroachDB. It weakens from strict serializability to what's referred to as serializability, again, at a cost of doing these a very expensive two-phase commit going across here, so multiple round trips traversing the planet. Now, what's nice about the CP model, what's nice about the single system image is that it is an over-conservative model. We don't need to look at our applications and figure out, will they be OK if I run it in this model? No, this model is very conservative. It mimics as if you're writing an application on your computer, even though it's distributed. So you can think of it as just totally consistent memory running on your local machine. So this is very easy to program, but it's very over-conservative. And in some cases, Spanner, as noted here, Spanner can take almost 100 milliseconds for that window of uncertainty. And so 100 milliseconds is a really long time for a single transaction. For one write in your system, that's a very, very long time. Ideally, we want these things to be sub-millisecond, right? So the second choice is what's referred to as AP systems, available under partition. Kind of the big players here are Bashow's Riak, Apache Cassandra, and Amazon's Dynamo, which is the system that inspired both of them. And the way these systems work is that if I'm talking to copy C of the database, I always work with C, and then C will asynchronously send its information to A and B. So this is nice, because writes happen locally on C. They're very, very fast. Updates are out of the critical path. They happen asynchronously. But obviously, the problem here is that since we're operating locally with asynchronous propagation, if I write something at C and I can't communicate to A, somebody at A may read a value and see a stale value. The other problem is that concurrent writes happening at C and A can generate a conflict, a write-write conflict. And now I have to decide which value I take. And we'll talk more about how that choice has to be made. And so what's nice about these systems is that they are available in the cap sense, but they're very difficult to program because you have to think about all these potential memory anomalies that might happen if the network goes down. And so a lot of people say, do network partitions happen? Well, in the data center, you can control a lot. They still happen. But if we're talking about like doing this from Oregon to Dublin, well, that's going to be a lot more problematic because things can happen. You're traversing many, many more networks to get there. And these networks are much higher cost in latency on the links. So this dichotomy is kind of referred to as CAP. It was a conjecture originally at PodC 20 in 2000. And then later it was proven. And it basically says you have to make a choice between consistent under partition or available under partition. CP is nice because it's high. CP has the problems of being high cost, have low availability, and has synchronization in the critical path. Where AP has low cost, there's no synchronization in the critical path. It's high availability. But the problem that you run into is anomalies. So for CP, the problem is it's too costly to do operations. In AP, you don't have that cost, but now you have anomalies. Okay? And so kind of what our approach tries to tell you is that this is a false dichotomy. We're academics. We love proving things are false dichotomies. And what we argue here is that no application will really fit into this one-size-all to be shoehorned into either CP or AP. If we think of, like, if I can make a contrived example using Facebook, this is probably not how it works at all, but I could imagine that the financial transactions around Facebook's ad service probably require a CP model because they're working with financial data, even though we've seen that many financial data models can work with AP databases. However, if I'm liking somebody's post, maybe that could be under an AP model where it doesn't necessarily need to appear immediately. And at OSDI, Usenix ATC this year, Facebook has an interesting post that says, they have a paper that shows through empirical analysis that the anomalies happen at like 4 nines. You see anomalies. And they say, well, the cost of actually making it so you never see the anomalies, it's too expensive because people will just refresh the page and the anomaly won't be there anymore. And so Facebook does an entire empirical analysis to show that even stronger models sometimes are too costly to implement, okay? Generally, to say if they wanted to provide causal consistency for all of Facebook. And so what we want to argue is that rather than try to take your application and say, what is the most available, least conservative model that my application works in, what we want to say is rather, my application requires a bunch of invariants to be preserved, so some invariants over the state. And what we want to do is we want to choose models that guarantee those invariants, but don't incur additional synchronization costs, like unnecessary synchronization costs. And so the approach that we're going to talk about today is called just right consistency. It basically says that application developers want to write invariants as if they're writing sequential programs. We'll show that invariants fall into two classes, either AP-compatible invariants, which are typically invariants that require one-way communication, or cap-sensitive invariants, which typically require two-way communication. And we'll see the difference between those two. And AP can be provided under AP. Cap cannot be provided without CP. And then finally, if I was to ask the developer to classify invariants into these two categories themselves, I wouldn't really be giving you much. And so what we want is we want a tool chain, a set of static analysis tools for our programs, for our languages, that allow us to look at the applications we've written and say whether they need stronger coordination or not. So we'll talk about all these. So I'm going to motivate all of this through an application here called FMK. I think you pronounce this Feia Medicine Kot, I think. And so this is Danish. So if you live in Denmark or you're from Denmark, Denmark has a card you carry, has all your prescription data on it. It has all your prescriptions, all your medications, everything. It's been running 24/7 since 2013 for the 6 million Danish citizens. This card is used for life cycle management for all of your prescription data. So getting a prescription, like filling a prescription, getting a prescription from a doctor, everything goes through this system. In the real world, it runs on Riak in Denmark. But we have a synthetic workload that we've built called FMKE. We have a paper about that allows you to run this on other databases if you'd like to see what this workload looks like. So rather than have a this is the moment of the talk where I get to snipe YCSB and say, rather than have some arbitrary benchmark that doesn't really model a real-world application, this is a nice benchmark that we built that you can use that models a real-world application. And basically, FMK is assumed to be correct in isolation, or correct sequentially. Every operation that it does, they assume that these operations will work fine if there's no concurrency in the system, so if it's not distributed. All right? So to talk about how this works, this is the API. So users can create prescriptions. This creates a prescription record, and then it creates a foreign key kind of reference in the patient record, the doctor record, and the pharmacy record. You can update prescriptions. That is, you can take a prescription and give more medications to it, so increase the amount of medications on the prescription. You can process a prescription, which says that you're going to decrement that amount and actually give somebody a physical prescription, medication. And then finally, there's a set of query functions, which we don't really talk about, but we highlight that it's in the API, so you know how to interact with it. So FMK asserts 3 invariants. The first is what we refer to as relative order or partial order invariant, which is basically referential integrity. And this says that if I create a prescription and I'm going to then update the patient record, I never want a situation where the patient record has a reference to a prescription that is not available yet. I haven't been able to get. The second invariant is what's referred to as joint update or an equivalence invariant. And this says that if I create a prescription and then I update the doctor record and the pharmacy record to reference it, if I see the reference in the doctor record, I have to see the reference in the pharmacy record. So this means that I want updates to happen together. So I want them to happen in order, and I want some of them to happen together. And then finally, the last one is I shouldn't be able to get the same medication more than once. And so this is what we refer to as the precondition invariant, which basically says if some condition is true, then I can do this other thing. So let's talk about these invariants in order, starting from the top. So the first 2 invariants fall under a pattern that's referred to as AP compatible. And this means that these invariants can be provided on a system that's AP, does not synchronize. You do not need spanner. AP compatible invariants have no synchronization in the critical path. Updates always occur locally. They are asynchronous. They happen fast. They're asynchronously propagated to the other copies of the database. And the compatible invariants are relative order and joint update. Now, before I talk about how each of these invariants work, I have to talk a little bit about the data model that this requires. So in a normal kind of database where you have mutable registers, something like this, I have 2 copies of my database. And here I can set the value to 1, and then I can send the value to the other copy. So at this point in time, both copies of the database have the value 1. Now, in a distributed system that does not have synchronization, such as an AP database like Cassandra, I can, at 2 replicas, service 2 updates, one setting the value to 2 and one setting the value to 3. Now, the problem I run into is that if I set the value to 2 and I set the value to 3, and I asynchronously propagate that message to the other node, I will just swap the values. Right? I'll swap the values. And the reason this happens is because these operations do not commute. I cannot reorder these operations. They have to happen in a particular order that will define what the outcome is. And so the problem here is that assignment required on a distributed database requires CP. It is an incompatible model for an AP database. And so the question we first have to ask is, can we build a model, a data model, that is AP compatible? Which basically means, can we make non-commutative operations commutative? So to give you another example, I do my concurrent setting of 2 and 3. I propagate the messages to each node. And now I have to make a choice. And that choice has to be deterministic. How do I pick the value that I keep? So if we're Cassandra, what we would do is we basically say every computer that performs writes takes a timestamp. That timestamp comes off the clock on the computer. And we pick the one with the greatest. Right? So that is deterministic. Given 2 timestamps, I'll always be able to tell you which one came later. But the problem is that this is a very bad model because, one, computers are very hard to synchronize clocks on. If you are running Spotify on your computer and you have a MacBook, your clock can skew. And then NTP will fix it. But you know when it will fix it. And it might fix it only within 1,200 milliseconds, but whatever, right? So synchronization of clocks is very bad. The other problem here is that if I just pick one based on time, that doesn't capture programmer intent. So if I change it to 2 and you change it to 3, 3 might be the right value, but 2 might have a higher timestamp because I set my clock into the future, or I have the wrong time zone, or whatever. So timestamps are bad. And so the question we ask is, can we be smarter about how we choose the value? And so if I was building an application to count something, I could say, well, always pick the greatest value, right? And so this is deterministic, and it encodes some sort of logic. And so what we want to do is we want to find a way to generalize this. So you don't have to do this. We already did this for you. We did this many years ago. We have this thing called CRDTs. And what these are data types that basically look like sequential data types, so dictionaries, lists, counters, booleans. But what they do is they come with a merge function that has a predefined way all of the things will merge. So you don't have to think about it yourself. So this encodes this. So if you have a set and you concurrently add elements, it will union them together. That is a deterministic merge if you never remove things. If you're going to remove things, then it biases towards concurrent adds winning. All of this is done, and I'm happy to provide references. We can't go into that. That's a whole talk in itself. So let's talk about, so that's the data model we assume. So we assume that all of the operations in the system commute. So given that, let's talk about relative order. So what relative order means, like I said before, I want to do something and create a reference, create an object and then reference it. What relative order basically means in a general, like kind of theoretic sense, is that I want to basically make an implication based on the ordering of some events. So in this case, let's pretend that I want to say that P implies Q. And to ensure that P implies Q holds, what I do is I make Q true, so the referenced object, and then I make P true. And now, on this node, since the events happen to this order, P implies Q holds. And on this node, where I send the updates to, since the order is the same, it's a compatible order, the implication still holds. The problem is that if I don't synchronize, if I don't add coordination, and Q arrives after P, then I violate that implication. I violate that invariant. So you're probably saying, this is a bit abstract. Let's talk a little bit more concrete. So if I assume that my database has a default administrator password on database A, I change it, and then I enable the login, replica A is fine. Nobody can log in with the default password. Now, replica B is fine as long as I deliver those updates in the correct order. Now, if I deliver them in the wrong order, there's a window where the login is enabled, but I haven't changed the password yet. So this is what we're talking about. This is referential integrity. It basically says that I create an object that I reference, and I have an object that causally is related to that. And so this falls under a consistency model that doesn't appear in many databases that's adopted by industry, unfortunately. But this is a consistency model that's referred to as causal consistency. It's based on causal relationships in this paper that's very famous, is kind of the genesis of that. This is the strongest available model you can provide under AP. And this model is sufficient for giving you referential integrity. So it says if you want referential integrity in Cassandra, you just need causal consistency. All right? So that's the first one. So the second one is join update. So to give you an example of what I mean by join update, I'm going to add a third node here, which is a client that's performing read operations. So in this example where I want to create a prescription, I create a prescription, I add a reference to it in the doctor record, I add a reference to it in the patient record, and then I add a reference to it in the pharmacy record. Now, since I have causal consistency, I will never have a reference to an object that doesn't exist, because I'll always deliver the reference first and the referencing objects after. The problem that I do run into is that if my client can interleave a read, I read something that from the application point of view is not consistent. I have an updated doctor record and an updated patient record, but I don't have an updated pharmacy record, because I didn't send those updates together. And so with this missing update, we want to basically say, can we do this all together or not? Yes, you can do this in AP. We can group these into a transaction. We can send the transaction together and apply it atomically. And then at every atomic application, we can do snapshots. And then we can guarantee that as long as those snapshots are delivered in causal order, everything will be causally consistent, and I'll never see the anomaly. So the two techniques I've told you, and so this is sufficient to provide the A in ACID. So this gives you just the A. And so these two techniques combined provide what we refer to as, this is the technique in the literature, it's called transactional causal consistency. This is the strongest model that's available under AP. And what it is the combination of all or nothing transactions, so this is snapshot reads, causally consistent snapshots with atomic application, and causal consistency. This is the strongest model you can have under AP. Okay? So you might say, well, what if I have to do something stronger? What about this case where I have to give people their medication at the pharmacy? And so these invariants fall under what's referred to as cap sensitive. So these invariants are problematic under AP systems. So if I want to prevent the case, so the case we're going to talk about is preventing giving somebody a medication more than once, or more than the number of times they're allowed to have it, rather, is a better way of saying it. So I'm going to start out with 3 copies of the database. They're going to start out with 2 available. They're all in sync. It's all consistent. They're going to start out with having 2 available medications. Now, at replica A, if a client issues an update that says, I would like to get one of those, fulfill one of those medications, it will check the condition. Is there one available? Yes, there is. And then it will perform the update and send it. And then at the end of the execution, the outcome says that, yes, all of the nodes have 1 prescription remaining. The system is consistent. So that's sequential. Let's talk about a concurrent. Let's add some concurrency. Let's make it fun. So we have 2 prescriptions. And now what I'm going to do is I'm going to try to fill one at this database. Maybe it's located in the US. And at this database that's located in Denmark, I'm going to add 3 medications. So that's fine, right? Because add will never cause the invariant to violate, because it only ever adds medications. It never removes them. And so this is fine. 1 goes away. We add 3. We get 4. It's perfect. Everything is fine. And so the way we think about this in the theory is that we say the precondition is stable under concurrent additions. So obviously, there's got to be a problematic case. Otherwise, this talk would be really boring. So what's the problematic case? The problematic case, obviously, is if I try to fill 1 prescription at the database in the US, and then fill 2 of the prescriptions at the database in Denmark. And so these 2 operations, since they're not synchronized, will both succeed, because the precondition matches here. Yes, I have 2. Yes, I have 1. Then we have 1. And at the end of the execution, we end up with -1 medications. And that is a violation of the application invariance. So what do we say? So the way we think about this, kind of in the theory of the execution, is that the precondition is not stable under concurrent fulfillment. So it is stable if I do concurrent adds. It's not stable if I do concurrent processing of the prescriptions. And so at this point, we have to make a choice. We're kind of back to that AP-CP thing, right? We have to make a choice. The choice is, do we prevent the operation from proceeding? Do we prevent the filling of medication to ensure the invariant synchronize and then have no availability if the network's down? Or do we allow the invariant to be violated, in which case it's not an invariant? I will note that in the real Danish National Healthcare Service, they go for the always available model, because they never want somebody to go into a pharmacy and try to get their medication and not be able to. So I think that's a very practical decision by the government of Denmark. We like that. And so you would say, based on this, I've just shown you this, the question you have to ask is, how can I, as an application developer, know what operations are safe and what operations aren't safe? This sounds hard, right? Do you have to draw one of these diagrams like I drew in OmniGraffle and like see and move the arrows around? That would be terrible. That would be terrible research. It would never get published. And so the way we solve this is that we have a technique. This is called SIZE. It stands for 'cause I'm strong enough. And this is an analysis technique that will generalize this execution to some precondition over U, some precondition over V, with some questionable invariant. And then it will perform an analysis and try to identify which combinations of things are problematic. So the way this works is it's done all through a complicated kind of like mechanism that leads into a solver, a SMT solver. And what it does is it looks at three things. It says, is the system correct if I run all of the operations by themselves, like sequentially? Okay? Now, if I reorder all of those operations, do I get the same outcome? So if I run A, B, and then I run B, A, do I get the same thing? Do I have convergence? Yes, that's fine, good. And then finally, what do? I look at every possible pair of operations that can be concurrently. You only have to do this for pairs. The big result of this paper is you don't have to do it exponentially. You only ever have to compare pairs. And what this will say is, if I only compare every possible pair of operations that can run at the same time, will I ever have an operation that will violate the invariant? And so if you do, if all of this passes, then your application is safe under concurrency. If it's not, it will tell you precisely the operations you need to coordinate on. Where do we want to go with this? Well, we want to automatically synthesize coordination. We automatically want to have it so we can generate some Java code. You throw it in, it hits Zookeeper or something like that, and it makes this safe for you. Right? And so this is basically mostly research with a small Java prototype that we're working on. We'll be working on over the next year, turning into a product. We've been working on the database first. All right. So I think I got like 10 more minutes or something. Well, I have more time to leave questions. And so basically, I'm briefly going to talk about the database part of this, not the analysis part, which we've been working on for the past 3 years. So the database is called Antidote. This database is an open source database. It's written in Erlang. It's on GitHub. It's been developed on top of the Riak core distributed systems kind of framework in Erlang. This is the same technology that's been used in the Basho's Riak database and a few other databases. And the technology is very nice. It's been used by the NHS for their National Health Service. It's used by the FMK, Danish one as well. So all of these systems take advantage of this underlying Riak core distributed systems framework that we've built on top of. Antidote is the only database that provides transactional causal consistency. So there's no other databases that have the combination of transactions and all or nothing transactions and causal consistency. And finally, we have like this alpha release that's out there. It's just kind of to explore. It's definitely do not run it in production, please. But we have an alpha release that you can compile and play around with and run, and it's all in Erlang, and there's some Docker containers and stuff that I can point you to at the end of the talk. So how does the architecture look? So here's our 3 data centers, our A, our B, and our C. These are clients that are talking to them. So each data center, this is designed, again, for geo-replication. Each data center has a series of nodes. So each data center will have 1 or more nodes, N1, N2, and then this blown-up node. Each node is responsible for coordinating transactions. All of the writes to the system are done as operations that are stored in an operation log. When you read, you materialize elements out of that log. We keep that log because of snapshots. You may have concurrent snapshots that are running at different read times. And so we need to have that log and build the snapshots. And we build these and prune them and things like that. Now, within the data center, so we expect you're running this logical data center. Inside the data center, the system provides strong consistency. So this provides very, very strong guarantees within the DC. On the wide area, this is where our protocol, which is called Cure, the protocol runs a causally consistent transaction protocol in the wide area. So within the single DC, you have strong consistency, and on the WAN, you have transactional causal consistency provided by our causal consistency protocol. So back to the data model. The data model is based on CRDTs. So this is not an arbitrary, like, I'm going to write some object that's just a binary blob. It's opaque. You actually have data types. So this looks a little bit more like Redis or Riak's CRDT interface. So you have 2 types of registers, which you just do assignments to. You have illustrator wins. This is a timestamp-based register. If you'd like to use that, that will arbitrate based on timestamp. That is deterministic again, but may not capture intent. We have a multi-value register, which is the typical Dynamo Riak style register, where at particular points in time, the register may have multiple values. We have sets that can only be inserted into. We have sets that have an add-wins bias under concurrency, which means that you can add and remove elements. And at any point, if an add occurs concurrently with the remove, it will bias towards the add winning, which is very close to sequential semantics. And then we have one that biases towards removals. We have a recursive dictionary that all of these types can be embedded in. So this would be like a JSON kind of type object, hash map. We have counters. We have a counter that can arbitrarily be incremented and decremented. We also have a restricted counter that maintains a positive, a non-negative balance. And the way this does this is it realizes that you only need to start coordinating once you get down to the limit. And so this is kind of the first data type that was built using that SISE analysis. So this is a specific case of that, special case of that. There's a graph API and a sequence API. This is the replicated growable array, which is basically a convergent CRDT list that has behavior similar to something like Google Docs. So it's similar to like a collaborative editing, where you'll arbitrate based on insertion order under concurrency, lexicographically ordering based on the node that's doing the update. OK, the API, what does the API look like? So this is Erlang. I apologize in advance. And so it's really simple. I'm just going to highlight kind of the bits here that are important. The first is that every object is identified by a triple of an object name, a type, and then a namespace. So this is similar to Cassandra's or Riak's bucketing. Since we're dealing with data types, the API you use to interact with data types is a operation-based API, where you say, like, perform this type of update. So if it's a set, you'd say insert into that set, remove from that set. If it's a register, you say assign. And so here, I'm just assigning the list of Michelle with michelle@blub.org to the object user1. And then I can read objects back. And you can provide a snapshot time if you need to, but that will automatically be done. So this API is extremely similar to something like Redis. I mean, this is like it's got all this Erlang nonsense in here with the tuples and all of that stuff. But the API fundamentally is an update read API once you get past the syntax. And so we could think this is very similar to Redis or React CRDTs. But what's really nice about this API is that in Riak, those updates would appear in any order. In Cassandra, those updates would appear in any order. But if you do this in Antidote, those reads will obey causality. So if you read an object and you later write another object, that object contains causal information linking it to the read. And so it will ensure that that object that you read is there before you're allowed to read that other object on the other side for the propagation. It will apply those updates in an order that is compatible with causal ordering or causality. Okay, so you get that for free. Program order, you just get the dissemination for free. The transaction API probably looks like any transaction API you've ever seen before. You start a transaction, you commit a transaction, and you interleave reads and update operations inside of that transaction. Pretty simple. Not a lot of fancy stuff here. Basically, transactions are disseminated in a causally consistent order. Transactions themselves are causally consistent. And all of the updates that occur in a transaction will be applied atomically. OK. So we'll look at some numbers. So these numbers are going to be more veered towards the algorithms and the theoretical stuff, not the actual performance numbers, because we haven't done any actual performance tuning to like the on-disk data structures or anything like that. So it's really important just to look at the trends here. And so we see that, so these are last read or wins registers. And we can see basically here, this is going from one data center of 25 nodes to two data centers of 25 nodes to three data centers of 25 nodes. And we see that the scalability here of the protocol is basically, as we grow the data centers, is near linear, which is really nice, which means that we can just kind of grow by adding data centers without paying a huge cost, because we're not having synchronization in the data centers until we need those CP-sensitive, the cap-sensitive invariants. So for the AP-compatible invariants, you take almost no performance overhead for that. And similar results, obviously, here for the, this is like not doing it. Similar results here for growing the cluster as well. So we can look at these results. So these results are comparing our protocol, which is called Cure, to the state of the art. So there's a bit to digest here. So EC represents a benchmark that is running eventual consistency. So it guarantees that it makes no guarantees on when the updates will be seen. The updates can be seen in any order. And there's no atomicity, no causal consistency, nothing. It's just eventual consistency. So obviously, eventual consistency has the best performance because it provides the weakest guarantees. That should be no surprise. So that's why EC is. Eiger and general rain, so EIGER is Eiger, the Eiger protocol. GR is the gentle rain protocol. These are two previous results in providing systems with causal consistency. And we see here that the Cure protocol, so this is a slight anomaly in the test, but for the most part, the Cure protocol is either the same or slightly better in terms of cost when it comes to Eiger and general rain. And so basically, the main difference here around this is that Cure is the only one that provides transactions, so we pay little cost in getting the transactions. And Eiger, general rain, and Cure have 3 different mechanisms for tracking the dependencies. So when I said that I have this dependency between P and Q, one of these objects needs to contain a bunch of metadata saying that it's related to P and Q, that's related to Q somehow. And so in that example, there's a variety of different ways that you can encode this stuff. People have been working on this for 10, 20 years to try to figure out how to do this efficiently. It's still an open problem. And so the game here is to try to get the cost as minimal as possible without basically violating causal consistency. And so this benchmark here is showing a comparison between Cure and eventual consistency for CRDTs. And there's an interesting result here that we can note. So the important things to look at here are the read-update ratios. So this is a high read workload. And this is a balanced workload of 50-50, read to write. And what you're going to see here is that in eventual consistency, in systems that use eventual consistency with those CRDTs, those commutative data structures, you have to send the entire data structure around the network all the time because you have no guarantees on ordering. And the guarantee that these CRDTs have is that every data structure that has some change applied to it is monotonically bigger than the previous one. So you have a data structure that's growing over time. And so if you have a very high write, if you have a very, so on these read workloads we see here, eventual consistency gets more, has different performance characteristics here. Now in Cure, since Cure has causal ordering, that means that if we send all of the updates to the data structures in causal order, I only need to send the delta, basically. I don't need to send the entire object. So Cure basically is going to do much better. Cure is going to have a much higher throughput on the writes because it doesn't have to send the whole object on the wire. It can send just the delta. But Cure is going to pay a performance penalty on reads because it needs to take all of those deltas and apply and merge them together to give you an object back, right? And so the trade-off here is between whether you're optimizing for the read workload, the read-heavy workload versus the write-heavy workload. Cure also needs to have this operation-based materializer for the log because given that it provides causally consistent snapshots, you'll have many snapshots running at different times, reading different versions of the objects, and so you need to be able to materialize objects that match those snapshots, that are compatible with those snapshots. Okay, future features. So right now, Antidote does not have replication inside the data center. It's been designed, the prototype has been specifically designed for scenarios where you have redundancy through georeplication, not redundancy within the data center. Now that being said, there's nothing that prohibits you from running 2 logical data centers in the same physical data center. It's the distinction here between within the DC and outside of the DC is that normally within the DC we provide strong consistency, and across DCs we provide causal. So if you're OK with causal within the data center, then you can run 50 copies of the database inside of one physical data center, and they'll look like logical data centers. So there's nothing shared. That's partitioned. Yes, that's correct. Yeah, that's just for sharding. And finally, for the database to provide you with ACID transactions, for the database to provide cap-sensitive invariants, you need ACID transactions. Our protocol does not. Our prototype implementation of Antidote does not have ACID transactions yet. And the reason is mainly because we've been focusing on the research contributions, not the engineering work. And because this is a known problem, it's just we need to hire somebody to go in and write the code. This is not an open research problem. So as academics, we don't write a lot of code, obviously. So we'll hire somebody to do that. So to wrap up, I think this is my last slide. Moving forward, what do we have? So we built a research prototype as part of a research project called SyncFree. We have a new research project called Meiklejohn, which is going to continue working on this. The goal was to build a database that had the least amount of synchronization possible while providing the highest guarantees. So we've been working on that for 3 years. It ended in January. The goal was that a lot of the features would end up in Bashow's Riak, but the architecture soon drastically kind of separated from that, and so we forked into our own thing. So we have roots with Bashow's Riak, if you're familiar with that. And a lot of the examples I showed you today came either from Angry Birds or the FMK system. So those were the partners for the research project. So we had a lot of work that was done with industry. Moving forward, we have a new project called Meiklejohn. This is investigating basically moving Antidote closer to the edge. So we'll be kind of moving it into data centers that are running at the edge rather than kind of a small amount of centralized data centers. We want to basically run hundreds of thousands of instances of the database. And so we'll be working on scaling the protocols to handle that. And finally, we're in the process of very close to obtaining seed funding to start a company. My colleague Peter is in the back there. He will wave. He is working on this with us. And so basically, we're hoping to, while we improve the research on the database, we're also hoping to kind of turn this alpha release into something that people can actually use that's valuable and kind of be the first database that has kind of these strong guarantees in the market for an AP database. So we have some code on GitHub. All of our stuff's up here. I'll put all of this. I'll tweet about all of this stuff later. But we have a website, AntidoteDB. We have a Docker container that you can download. You just run it, and it will pop you into a console for the database. You can play around with it. You can run a bunch of them with Swarm or something like that and have them communicate if you want to see the protocol in action. We have an interactive tutorial and a JavaScript app that runs like a to-do app on top of this that I can point you to, too. So there's a bunch of stuff that you can play around with. And that's basically it for me. We'll be hanging around later if you want to come talk about Antidote or talk about the protocols. Obviously, today I couldn't go into the details of how CRDTs work or how the transaction protocol works. But what I really wanted to do was sell you on the vision that you don't need to make this choice between CP or AP anymore. We should be thinking about it more granular and saying that that is a choice that we really need to make for particular parts of our application. And ideally, we want a system that allows us to make those trade-offs in the way where we get the most scalability. OK? Thank you very much. So I think I have, yeah. Yes?
Question, do you have the protocol somewhere on the website where we can read and go over this?
So there's a published paper at ICDCS 15 on the protocol. It's called Cure. I'll happily point you to it. But yeah, there's a published paper that's available online with the protocol. The other thing I should say is if you're interested in doing research, and the other thing that might be interesting is all of these protocols actually are implemented in our database, and they're all configurable. So if you actually know a little bit of Erlang, you can go in there, you can run the different protocols and see all this stuff. So the platform is actually kind of dynamic in that way as well. Obviously, we recommend you use our protocol because it got published and it's been demonstrated that it is now the state of the art. But it's a nice thing to have. Yes?
You mentioned earlier in one of the slides that you're running some tools to see the application can actually take advantage of the database, or if it doesn't make sense.
Yeah, the size analysis.
How does that really work, right? Like from my perspective, right, there's an application, there are 500 developers writing code. How would they actually be able to?
Yeah, so there's a few pieces. There's a few pieces of the puzzle here that I didn't talk about. So the size analysis is a proof theory. Popple 15, it's called Because I'm Strong Enough. It is a proof theory about determining, demonstrating that you only need to examine pairs of concurrent operations to find these problematic cases. Now, size is not a tool. It's a proof theory. If you read the paper, it's going to be a lot of math and a lot of separation logic and stuff like that. And so more practically, what we have is a prototype. There's a video on YouTube. If you look for SciZ, I can tweet about it later too, that shows. And the way it works is that it's a multi-step process. So you take a Java application, you use annotations to put in annotations in first-order logic. That first-order logic defines the effects that the operations have and the invariants that should hold. And then the analysis tool will basically will analyze that file. It will basically produce an input to the Z3 stat solver, and then from Microsoft, and then it will attempt to solve the constraint and figure out if these 3 properties are satisfied under that. So that is the current status of things. But the tool is open source, but it's very brittle at this point. It was a proof of concept to show that we could go from actual code to the analysis. But there's questions of whether that tool will hold under sufficiently complicated higher order programming and things like that. So we haven't gone that far yet, but right now it's a simplistic version of this. And so the example of the video that we have is maintaining a positive balance for a bank. And so it will basically show that the only operations you need to coordinate on are operations for the same account with concurrent withdrawals. So 2 withdrawals are problematic only if they're on the same account, but a withdrawal and a deposit on the same account you don't need to coordinate for. And so the tool will demonstrate that it can narrow it down to that counterexample and give you that counterexample back and say you need to coordinate for this operation or you have to remove this operation in your app to be safe. Anybody else? OK. Thank you very much.